Now let's put a graph into memory. We will look at the same graph drawn 3 different ways. This is one graph shown 3 ways side by side. The picture, the matrix and vertex 2's chain. Watch how the same fact looks in each form. The left picture draws the graph directly. Vertex 2 is colored, and it has 3 edges going to vertex 0, vertex 3, and vertex 4. The middle is the adjacency matrix. Row 2 is highlighted, and it holds 3 ones in columns 0, 3, and 4. Those are exactly vertex 2's 3 edges. The right side is the adjacency list. Vertex 2's chain, written edge at index 2, has 3 nodes, one to vertex 4, one to vertex 3, and one to vertex 0. So the same fact takes 3 shapes. The picture shows 3 edges, the matrix shows 3 ones in row 2, and the list shows a chain of 3 nodes. Every representation in this chapter is just a different encoding of the identical graph. The adjacency matrix answers one question with one cell. M at row I column J is 1 when the edge from I to J exists, and 0 when it does not. The whole thing is one contiguous n by n block on the heap, stored row by row. Because the matrix is stored row by row, the address of any cell is simple arithmetic. The address of M at row I, column J is the base address, plus the quantity I times n plus j times the size of one int. That is chapter 2's address idea in 2 dimensions. Now look at the shape of the table. It mirrors across the diagonal. M at row 0 column 2 equals M at row 2 column 0, and both are 1. That mirror is the undirected symmetry invariant made visible. One caution about space. You may think an empty-looking graph costs little. But the matrix uses big O of V squared space, even if it holds no edges at all. All 36 cells exist here, whether they hold a 1 or a 0. You pay for every possible pair, not just the real ones. Let us predict before the reveal. Vertices 1 and 4 are not connected in this graph. So what are M at row 1 column 4 and M at row 4 column 1? Pause and answer. Both are 0 because there is no edge. And notice they agree with each other. Even a missing edge keeps the matrix symmetric. The adjacency list is an array of n-head pointers. Each slot, edge at index u, starts a chain of that vertex's neighbors, with one edge node per real edge. Take vertex 1, which has degree 2. Its chain, edge at index 1, holds 2 nodes, one to vertex 3 and one to vertex 0. Now vertex 2, which has degree 3. Its chain, edge at index 2, holds 3 nodes, one to vertex 4, one to vertex 3, and one to vertex 0. Each chain costs exactly its own degree, nothing more. Count all the nodes across the 6 chains and you get 14, which is 2 times the 7 edges. Each undirected edge puts exactly 1 node in each endpoint's chain. That is the list consistency invariant, counted rather than just stated. One caution: you may think a friendship is stored once. But an undirected edge is symmetric, so it must appear in both endpoints' chains. Add 4 to vertex 1's chain, and also add 1 to vertex 4's chain. Miss the second, and the edge disappears from one side. The incidence matrix is a third view. Its rows are vertices and its columns are edges. M at row V column E is 1 when vertex V is an endpoint of edge E, so every column has exactly 2 ones, because an edge has 2 ends. Read the columns first. Every column sum is 2, because an edge always has 2 ends. Read the rows next. The row sum for vertex v equals the degree of v, so you read a vertex's degree straight off its row. And there is a directed variant. You write -1 at the tail and +1 at the head. Now the cost. This form uses big O of v times E space. That is always bigger than an adjacency list, and bigger than an adjacency matrix once E exceeds v. So it is rarely the default. It is good mainly for edge-centered algorithms, where the edge is the thing you iterate over. For our work, the adjacency list stays the practical choice.